I'm here with Shwetak Patel, Professor of Computer Science and Electrical Engineering at the University of Washington, and Desney Tan, a Principal Researcher at Microsoft Research, who are going to tell us something about exciting developments in the area of wearable health monitoring and the importance of collaboration. Shwetak, Desney, welcome. I've just teased the viewers with the notion of collaboration, and I know that's an important part of your message, but I want to get into your past research. So Shwetak, your group has done a lot of research using sensors to measure energy usage at home. What kind of apparatus do you use?
Yeah, so a lot of our energy work has been looking at how do you reduce the number of sensors that you deploy in a home environment to really make it practical. So it's hard to imagine somebody installing a sensor at every single appliance, and some of the appliances are in walls, so it's hard to pull them out. And so the apparatus that we have built is a single device that plugs into one outlet that can measure the energy usage in the entire home.
And what kind of signals does this sensor detect?
So the way this works is that, traditionally the way you would do energy monitoring is you would look at how much power might be used in the house and then try to figure out where the power might be going. So if you see a 100-watt device turn on, then that might be a light bulb. But the problem is that that device has to be installed at a particular location that might not be easy to install. And so this device is a device that plugs into a single outlet, and the signal it actually uses is not power at all, in fact. It actually uses electromagnetic interference that comes from the operation of electronic devices. And that signal actually tells you a lot about what device it is and how it's actually operating.
And how do you get the information on energy usage from, am I right in saying there's a noise?
Yeah.
And can you explain that?
Yeah, so the concept of electromagnetic interference or noise is what happens when an electronic device is operating. So the power supply that operates a laptop or a television or any consumer electronic device, when it's operating, it has a side effect of creating electromagnetic interference. And often people don't really think much about it. They usually think that this is a nuisance. But it turns out when you look at that signal, it can tell you a lot about the device itself. So you can use it to say that, oh, you know what, that noise signature actually looks like a television or a light bulb or a computer. And then that allows you to break down the energy usage in a different way than where others have looked at how to do this.
And how do you actually see these results?
So the way what happens is, there's a device that plugs into an electrical outlet. The device connects to the cloud where the data is being streamed to the cloud, and the machine learning algorithms are in the cloud. And what the user sees are a variety of different user interfaces. So one user interface could be on a tablet device. It gives you a breakdown of the electrical devices in your home and what percentage of the power is going to each one of those devices. So at any given moment, you can get a sense of what's on, but also what percentage of your energy usage is going to these various devices.
And how does that relate to the wearable health monitoring?
Yeah, so the trick or the technique or the fundamental concept here is looking at a signal that a lot of people haven't really looked at, or in fact, in this case, we've turned the problem on its head a little bit, in that the signal source is something that people often ignore. The noise is something, why do you even care about the noise? The noise is things that people want to cancel out, right? And here, the idea is that, well, we can take advantage of this signal source that we haven't really explored in new ways. And when it comes to health monitoring, well, there's ways that we've monitored the physiological condition of the body. But what if we look at that in a different way, similarly how we've looked at the power line? So what are some other sources of signal on the body, but also things that we've ignored on the body? They may actually tell us a lot about our physical health.
And so you can use sensors in your smartphone?
That's correct.
Can you give us an example?
Yeah, so one of the things that we've been doing is looking at, well, how do you build sensing capabilities on a mobile device for physiological monitoring? And one of the challenges here is just like in the home space. You can't put a sensor, everywhere on the body sometimes. Sometimes you can't put a device that you have to plug into a smartphone or a mobile device. And the idea here is that how do you transform the mobile device itself with the sensors that are already on it, look at signals that come into that to give you physiological information. And so how do you transform the existing sensors on a mobile device into a physiological health monitor? And so we've been working in this space, looking at a variety of different conditions.
I'm guessing this mobile health monitoring will be extremely valuable in developing countries, am I right?
That's correct. So one of the applications we've been working on is doing spirometry. In other words, a device for basically measuring lung function for people with chronic asthma, COPD, or other pulmonary ailments. And if you look at pulmonary conditions outside the United States and Europe, it's actually a fairly a big concern. And so by driving the cost down and basically creating a capability on a mobile device that people may already have, you have this hope of doing sensing anywhere in the world.
Desney, you've sat there quietly while Shwetak's talked about his noise and the health applications. So where did your journey begin?
That's great. So fairly similar journey and parallel journey to Shwetak's. Where we started was, as Shwetak took the home as his machine and where he started his sensing work, we started with the body. And in fact, we've taken a very parallel path and have ended up in roughly the same place, which is what has made this collaboration so productive. But very early on, we made the same basic observations that Shwetak had in the home, in that the body, albeit a more complex machine than the home, was emanating a lot of different signals. And very early on as well, in parallel with Shwetak, we had realized that turning that noise that most people treat these signals as being as our true signal was actually quite productive. And so we played around with a bunch of different ideas. We started with brain-computer interfaces, the notion that as your brain functions, some of the electrical activity leaks out through your skull and your scalp, and that we can sense this from the outside. We moved on to a whole bunch of different mobile interaction scenarios where we took those sensors and we put them on different parts of the body, started sensing muscle activations. Again, the electrical signals that activate your muscles leak out through the skin, and you can sense that. And so detecting things like finger gestures, fine-grained finger gestures with a very simple armband, rather than instrumenting the fingers, which we don't think is reasonable in the real world. When we first met Shwetak, we started to take some of the work he'd been doing in the home with electromagnetic interference and applied that to the human body as well. It turns out that the human body is a wonderful antenna. You and I are picking up signals right now as we speak because all the appliances and the power lines are emanating all this electromagnetic noise. And based on that, we can detect things like the posture and the gestures that users are doing, the location that they happen to be in at any given time. And then we've played with acoustics as well. It turns out that if you model the human body as a big bag of water, which essentially we are, you'll realize very quickly that sound travels through us, not just electromagnetic noise, but sound travels through us fairly nicely as well.
Okay, so you're basically taking the human body as a signal generator, using various wearable sensors to detect body signals. At some point, you recognise that these can be predictive of health and diseases. You've also come up, obviously, you've got the wearable devices like the band. Can you share some of the health metrics that this device offers?
Sure. So the Microsoft Band is available on shelves today. I feel like a little bit of an advertisement here. This is a product we launched at the end of last year. And it's a product with two core value propositions. One is it's a productivity device. And so this hooks up to my phone. I happen to carry a Windows phone, but it also hooks up to the iPhone and Android phones. And it gets my email and my messages and my calendar reminders. It also allows me to pay for stuff. So I can walk into a Starbucks coffee shop, the ever important cup of coffee, and I can pay using my band. On the other side, it's also a health and wellness device. It keeps me more healthy, which is the topic we're here to talk about. It's got a bunch of sensors on it. It's got your traditional accelerometer, gyro, to be able to do activity sensing. Pedometry counts the number of steps I've taken during the day. Interestingly, and this is a bunch of work we did, it also is able to detect when I'm exercising, to classify the exercises I'm doing, and in fact to count reps. So I can be doing bench presses or push-ups or sit-ups or jumping jacks, or any number of exercises, and this thing will help me log those rather than me having to scribble it down in my notebook. It's also got a heart rate sensor on it, which allows us to then infer how many calories I've burned as I go about my day and as I exercise. And the combination of sensors also tracks my sleep, which has been quite interesting in this trip as I get over jet lag and sort of try to find normal sleep routine again.
So, I understand you and Shwetak have collaborated on a new wearable health monitor or device that goes beyond the capabilities of the band. Can you say just a little bit about that?
Sure. So one of the fun things about research and the way we bridge from the academic to the industrial research to the product development is that, when we got done working on the band, we sort of popped out and we took a step back and we said, okay, what's the next step here? And we looked at a fairly high level at the state of healthcare and clinical conditions. And if you plot this out, you've got a couple of large conditions. You've got cancer, which is a large pocket of disease. You've got cardiovascular health, and then as Shwetak alluded before, you've got pulmonary health. And then you've got all others sort of as a very secondary set of conditions. And so we've been working on the cardiovascular health space together, and we've got a set of devices that we've been working on to be able to more continuously track, monitor and predict cardiovascular disease. And so with these new metrics, we can sort of not only allow people, patients who have been diagnosed with a certain set of conditions to continue to track and monitor their progress of treatment, but we can also start to predict even before detection the condition so that we can fix it before we would normally try to fix it.
Of course, of course. Oh, that's wonderful to speak to you both, and thank you for stopping by and talking to us about the future of wearable health monitoring and value of collaboration as well. Desney, Shwetak, it's been a pleasure. Now, we're going to take you to the demo floor, where Scarlett Schwadersky-Grosch has taken on 2 demos, one that demonstrates a technique that enables one to fabricate prototypes quickly, and the other enables her to make circuit boards fast.